Hello, my name is Michael Kim. This is my lab report 5 for Physics 2212, section X06. To start, the purpose of this lab is to use experimental data to calculate how long it takes for a magnet to fall through an aluminum tube. We also aim to create a computational model using various fundamental principles to replicate the experiment, and we try to compare our computational model to that of the experimental model. The results I got on my experiment and my computational model were that my average experiment time was 1.428 seconds, while the computational model was predicted at 1.405 seconds. As for the fundamental principles we use throughout this experiment, the Biot-Savart law is used to calculate the magnetic field of our dipole magnet. We use Faraday's law in order to aid in calculating the current and in the infinitesimal rings of the tube. And we use Newton's second law in order to update the position computationally of our magnet in the computer simulation. For some observations that I made while doing the experimental portion of the lab, the magnet appeared to fall through the tube at a constant velocity. While falling, the magnet would rotate and finish at an angle perpendicular to its origin. And if the experiment were to be done with a ferrous tube, the magnet would likely just attract to the side of the interior wall and stick there. Here are some experimental results and the measurements I had for my lab. As you can see in the video to the left, the magnet falls straight through. And as for the experimental times, the average was 1.428 seconds. And the dimensions of the tube were shown to the right, which are important in calculating the computational model of the experiment. When it comes to the process that we will use when coding the experimental version into the simulation, in order to calculate the magnetic force as the magnet falls through the tube, flux for infinitesimal rings within the tube need to be calculated, and as shown in the image to the right, which is the resulting image from the coding section, blue and red rings show the magnet falling through the tube. Here I'll be showing some important coding aspects of the simulation. In the first section, the Biot-Savart law is used to calculate the magnetic field, and in the second section, the flux is calculated with respect to change over time and is used to calculate the current rings. Here, the first image on the right shows the calculation of magnetic force on the magnet per ring as well as the current of the given ring of tube. The second section calculates the net magnetic force that will be used in the net force calculation. And the third section uses the Newton's second law in order to update the position of the bar magnet over time. The resulting image from the coding section is shown to the right, and as you can see, the magnet begins to fall through the tube at a constant velocity until it reaches the end. The computational time is off by approximately 0.02 seconds from the experimental time, and my estimation is that this is a result from human error and the timing and order from when the magnet hits the outside of the tube. As for what would happen if the resistivity of the conductor reduced to as close to zero as possible, the induced current would increase with lessened resistivity, and thus the magnetic force increases and the magnet falls slower. And as for what happens if holes or slots were cut into the tube, there would be less complete rings, and therefore the resistivity would increase. Thus the induced current will decrease, the magnetic force will decrease, and the magnet will fall at a quicker rate. And that is all for my lab draft 5. Thank you for watching.